Okay, this is practice quiz 2, number 2. It says solve a differential equation by finding an integrating factor and then using exactness. And then verify your answer is a solution. So here's our differential equation here. So this guy here would be my m, this would be my n, so let me mark that. Okay, there's my m and n. So it's claiming that we need to find an integrating factor, therefore it should not be exact right now. Let's compute my and mx. So computing my and nx, we get, so for my, here's my m over here. I could multiply that y in if you wanted to here, but I'm just going to use a product rule, so it'll be derivative of first function, so derivative of y with respect to y would be 1 times second function plus first function, so y times derivative of second function, but the derivative of this function here would just be 1, so it would just be this. So combining those, it would be x plus 2y plus 1, so let me write that here. Let's find n derivative with respect to x. So it looks like there's going to be 1 here. So it's just 1. So you can see that the differential equation is not exact at the moment because my does not equal nx. So let's note that. So we can note my not equal to nx implies differential equation is not exact. So we have to find our integrating factor. So we're going to use the method we developed in the last section. So there's 2 cases we need to check here. So let me write the 2 cases. So our first case is the integrating factor is u of y, which equals e to the integral of h y dy if h of y equals 1 over m nx minus my is a function of only y. And the second case we need to check is the following. So it's the integrating factor is a function of x if it equals e to the integral of h of x if h of x equal to 1 over n my nx if this guy is a function of x only. So let's check the hy guy first. So we have our my up here, our nx here, and our m. So let's compute this. So note. Okay, so computing the 1 over m nx minus my. So the m is this guy up here. So it's 1 over y times x plus y plus 1. Then times nx, which is 1, minus my. My is x plus 2y plus 1. Have it here. So simplifying this, so I messed up here a bit. Simplifying this, we get negative x plus 2y over y times x plus y plus 1. And this needs to be a function of only y, but you can see it has an x in it also. So this is not a function of only y. Therefore, this h of y guy is not going to work. So let's check the h of x guy, the 1 over n guy, this one next. So if this is a function of x, then we can use this as our integrating factor. Let's check that one next. Okay, so now checking the 1 over n my minus nx. So the n is x plus 2y, so it'll be 1 over x plus 2y. And then it's my, which is this guy here, so it'll be x plus 2y plus 1. Then minus nx, which is 1. So simplifying that becomes then x plus 2y over x plus 2y, which reduces to 1. But the number 1 you can think of as a function of x or a function of y, it doesn't matter. So you can think of this as a function of x, so therefore this works. So therefore we can choose our h of y, sorry, our u of x to be e to the integral of h of x dx, where h of x is this guy here. Okay, so let's continue. I'm out of space here, so let me erase a few things and we'll continue. Okay, so summarizing, our h of x is 1 then, so our integrating factor will be e to the integral of h, but h is 1 here. So it'll be integral of 1, which would just be x. So our integrating factor is e to the x. So here's my original differential equation. So I'm going to multiply both sides by our integrating factor. So let's do that. So multiplying both sides by our integrating factor, we get this then. So this new differential equation should be exact. So let me call this guy here m tilde and this n tilde. Okay, and let's show what's exact. It should be exact, but let's just prove it here. So let's look at m tilde with respect to y first. Okay, so doing with respect to y, so I'm going to use a product rule. So it'll be derivative of e to the x y with respect to y would just be e to the x times second function here, plus e to the x y times derivative of this guy with respect to y would just be 1. So then you can write this as e to the x times x plus 2y plus 1. I just factor the e out and then combine the y with y to make 2y. Okay, let's next do n tilde with respect to x. Okay, so we're taking derivative of this guy with respect to x. So e is my first function and this guy x plus 2y is my second function. So it'll be derivative of e to the x with respect to x will be itself. So times second function plus the first function e to the x times derivative of second. So derivative of x plus 2y with respect to x is just 1. Then I can factor the e out and then we'll get the following. Looks like we get the same answer. Yeah, we get the same answer. So therefore we've shown that this new differential equation is exact. So now let's use exactness to solve for it. Okay, let's keep going. Okay, so since it's exact, we should be able to find this parent function f. So we can find it by integrating my m tilde with respect to x. We can also find it by integrating the n tilde with respect to y. So let's do the m tilde guy first. So I'll be integrating then this guy. Now I'm going to actually multiply this e in, which I've done over here. So multiplying it times that, times that, times that. So times this guy will be xy e to the x plus y squared e to the x plus y e to the x dx. These last two guys are going to be fairly easy to do. This one's going to be a slight problem. We're going to have to use integration of parts. So let's do that. Okay, so we're going to integrate, focus on this guy here. That's going to be the hard one to integrate, so I have it over here, that part. I'm going to have to use integration of parts on it, so just to review, integration of parts says the integral of u dv equals uv minus integral of v du, should be du here, sorry. Okay, so let's make some assignments here. So I'm going to say, it's going to let u equal x, y. So taking derivative now on both sides with respect to x, we get, so we get then du dx, derivative with respect to x is just going to be y. So then solving for du will be y dx, and my dv will be the e to the x dx. So I'm going to write that here. Then we're going to integrate both sides. So integrating this side does get v equals integral of e to the x dx. But the integral of e is itself, so it's going to be v equals e to the x. Okay, so making the substitutions up here then. So let me do that. So my u times v, well, u is xy, and my v we just said was e to the x, so this is my u times v. That's going to be subtract integral of v du. Let me write that. So v du, well, v is e to the x, du is y dx, so it's going to be integral of y e to the x dx. So we're integrating with respect to x, so the y can come outside the integral, and it'll be integral of e to the x, which is just going to be itself, so hence we'll get the following. So I'll get this then, xy e to the x minus y e to the x. Okay, that's going to go in place of this guy when I integrate. Okay, I'm out of space here, so I'm going to erase a few things and we'll keep going. So summarizing, we have the integral of xy e to the x is equal to xy e to the x minus y e to the x. And we found our small f was equal to this. Okay, and that's my differential equation up here. So let's break this integral up. So doing that we get, so breaking up we get this. This one we found up here, and y squared is a constant, so it's just going to be this is going to be just y squared e to the x, and it's going to be y e to the x. So let's make those substitutions. So substituting and integrating, we get, so making the substitutions, we get xy e to the x minus y e to the x plus y squared e to the x plus y e to the x plus a constant here, but the constant is going to be a function of y. So notice these two cancel, and then the guys remaining, they have an e in it. Let's factor the e out like I've done here. That'll be xy plus y squared times e plus cy. Okay, now let's find f by integrating my n tilde guy here. So let's do that next. So small f then will be the integral of n tilde respect to y, so integrating this guy. So it'll be this. Let's multiply this e in here, and then we'll integrate. It's multiplying the e guy in, but we're integrating with respect to y here. So the x e to the x is just a constant, so when I integrate it, I'll add a y there, and when I integrate this one, it'll become y squared. So let me write my answer down here. So I'll get this. So again, this is like a constant, so I'm just going to add a y to that one, and then integrating 2y becomes y squared. I can pull out the e like I did up here. So doing that, we get then. So I get this. So now we're going to compare our f's. So we got this one here and the one up here, and they look identical. So in particular, we can choose my cy function to be 0 and my cx function to be 0. That's fine. So therefore, we found our small f then. So hence our f function will be xy plus y squared e to the x. So the general solution then for this differential equation will just be replacing the f with the c. So let's write the general solution. So here's our general solution. C equals xy plus y squared times e to the x. So the last part of the question was to verify that this is indeed the solution to the original differential equation. So let's show that now. So I'm out of space now, so I'm going to erase some things and we'll continue. Okay, so the last part is to verify that this guy is a solution of the original differential equation. This is the original differential equation here. Let's first solve this original differential equation for dy dx. So let's divide both sides by dx first. So dividing both sides by dx, I guess it'd be here also dx. 1 and 2, but still 0 on that side. So then we want to take this guy over here. So doing that, we get then. So again, dx over dx is just 1 here. So moving this guy over here will become minus. So I'll have x plus 2y dy dx equals this guy. Then we can divide both sides by x plus 2y to solve for dy dx. So doing that, we get then. We have our dy dx equals this guy here. Okay, so now we're going to show that this guy here has the same derivative as this. That would verify it's a solution then. So let's take our solution here. Well, the thing we're trying to show is a solution. Let's take derivative on both sides with respect to x. So So now I'm going to take derivative on both sides of this guy here with respect to x. So here we're assuming that y is a function of x. So we're going to have to use implicit differentiation when we take derivative with respect to x. So derivative of a constant will be 0. So let me write out what we'll have here. So taking derivative, so derivative of c again is 0. And then you're going to have to take derivative of this side with respect to x. So I'm going to use the product rule, so it's going to be derivative of the first function, so think of it as the first function there. So, but the derivative of the first function here, inside there we got another product. So we're looking at this guy here. So it'll be derivative of x, which is 1, times y plus x times derivative of y with respect to x, so it'll be dy dx. So that's a product rule on the xy guy right here. Then the derivative of y squared using implicit differentiation will be, or chain rule, be 2 in front, 2y times dy dx times e to the x. So that's the derivative of first guy times e, plus first function, which is xy plus y squared, times second, but derivative of e is itself. Okay, so let's keep going. Yeah, so this again was a product rule here. So, alright, now I'm going to divide both sides by e to the x. So divide by e to the x, so it would be divide by e to the x here, here, and here. Pretty much the e to the x's will just go away. So let's keep going. So I get this. And now I want to, basically I want to solve for dy dx, and I want to show that it ends up being this. If I can show that, then I'm done with my verification. So let's isolate the dy dx terms. Okay, so I moved my the dy dx terms over to the side, so I got this then. Let's factor out this dy dx on this side, so doing that we get then. Okay, so I factored the dy dx out on the right here. I've also pulled the minus sign out, so I got minus x plus 2y dy dx. On this side I pulled a y out also, so I factored it out here. Then I can divide to solve for dy dx, divide by minus x plus 2y, so doing that we get. So we have then dy dx equals this guy here. Now this minus sign down here you can bring up to the top. Then looking at this guy and comparing it with the one up here, they're the same. So they're the same. So that means that this guy here is a solution of our differential equation. So I verified it. Okay, so we're done. So let's leave the video there then. So that completes the problem.